Okay, so we're looking at graphs and symmetry. And so we're going to be graphing equations by plotting points. We're going to be able to find intercepts of a graph by looking at it. We're going to be able to find intercepts of a graph by looking at the equation. We're going to test equations for symmetry across the x-axis, the y-axis, and the origin. And we are going to look at graphing key equations. So there's certain equations that you should know what the shape of the graph looks like. Okay. So finding intercepts. Of an equation. So when we're talking about intercepts, we're talking about values. If we graphed the equation, it's going to either cross or touch the x or y axis, depending on if we're looking at the x-intercept or the y-intercept. And so if you're looking for the x-intercept, so the place the graph touches or crosses the x-axis. So later on, probably next week, we're going to see how to tell by looking at, when we find those values, if it's going to touch or cross the x-axis. And that has to do with multiplicity of a factor, a zero. But anyways, if you're touching the x-axis, anytime you're touching or crossing that x-axis, that value of your y value is always 0 on the x-axis. And so knowing that y is always 0 on the x-axis defines the place where it's crossing or touching. You're going to let y equal 0 and solve for x. And so once we do that, depending on what type of equation we have, we would go about solving for our variable that's left. Y-intercept, almost the same kind of idea, but this time if you're looking at the y-intercept, that's where a point or the graph is touching or crossing the y-axis. The value of our x, the value of x for that point is always 0. So we're going to let x equal 0 and solve for y. Okay, so for example, if it asked us to find the intercepts and graph each equation by plotting points, be sure to label the intercepts. Okay, so we're going to find intercepts and graph. And so if we're looking at the following, let's say y is equal to x squared minus 9. So if I wanted to look at the x-intercept, again, we're going to let y equal 0.
I'm sorry, can you go up for a second just so I can take a picture? My pen ran out and I had to find one.
Yeah.
Thank you.
Yep. So we're going to let y equal 0, and we're going to solve for x. So doing that, just putting y equals 0 in that equation, we get 0 is equal to x squared minus 9. And so looking at the type of equation we have, it's quadratic. And so there's a couple ways that we can solve quadratic equations. Here's my green. And I notice I can either factor this, or I notice that I have a perfect square. I can use my square root method. So either way, I would get the same result at the end. I'm just going to factor it, I guess. So 0 is equal to, this is a difference of squares, so x minus 3, x plus 3. So I notice that x is equal to 3, setting x minus 3 equal to 0, and x is equal to negative 3. And so y-intercept, we're going to let x equals 0. And solve for y. So we have y is equal to, so wherever you see an x, you're going to put 0 in. So we have parentheses squared minus 9. So if I square 0, I get 0, and 0 minus 9 is negative 9. So I get y is negative 9. So basically, we found 3 points that are on our graph. We found that 3, 0 is a point. We found that negative 3, 0 is a point. And we found that 0, negative 9 is a point on our graph. So let's plot those. And so this is where it's helpful that you know what the general shape of y equals x squared minus 9 is, or you know what the general shape of a quadratic. And so quadratic equations are parabolas. So they're either going to face up or they're going to face down. Later, at the end of the course, we'll look at parabolas that face left and right. So I actually know what the shape of this is. It's a parabola, and I know that this here is the vertex. If I didn't know that, just from previous courses, I could plot some more points and kind of see that that's where it's going to end. Later on, we're going to look at it being in vertex form, which it is, and knowing that. And we're also going to be looking at shifting and transformations of graphs. So for instance, if I plugged in 1 for x, I would get y is equal to 1 squared minus 9. Well, 1 squared is 1, 1 minus 9 is negative 8. So I know at 1, I have a point at negative 8. Oops. So I could see that this is going to give me points in here, and that nothing's going to happen where it's going to go down and dip below this. Notice that this is symmetrical. This graph here, if I took my y-axis and I treated this as a piece of paper and then I decided to fold my paper along this y-axis, this side of the graph on the one side of the paper is going to line up with the other side of the graph. And so this is symmetrical across the y-axis. Okay, so notice that any point here, like our point 3, 0, in order for it to, if we fold the paper, in order for that to be a point, notice that's negative 3, 0. So this point we just found here, which was 1, negative 8, if I folded my paper along that line, I get another point that's on the graph. Well, my y value, notice, is the same there. It's negative 8. But my x value is not 1 anymore, it's negative 1. Same thing here, my y value is the same when I flip it across the y-axis, but my x value just changes signs. So that's actually a rule for something to be symmetrical across the y-axis. If xy is a point, then negative xy is also a point on the graph. So rule. If a graph is symmetrical, across the x-axis, I'm sorry, not x-axis, the y-axis. We'll talk about x-axis in a second. Then if, and maybe we can call it AB. If AB is a point on the graph, so is negative A, comma B. Another way to think of it is if xy is on the graph, then we also know negative xy is on the graph. So in a way, if we know that a graph is symmetrical across the y-axis and we start plotting points, we know double the points. So if I start plotting points like we did here, we found 1, negative 8 was a point, then we know negative 1, negative 8 is a point. So it would help us, and it makes it faster to graph. Okay, so let's talk about symmetrical across the x-axis. Actually, before we do that, let me also give you another rule. So another rule, if this is the case, if f of x is symmetrical across the x-axis, symmetrical. And I said x again, I meant y, across the y-axis. Then we know that if you plug in negative x, wherever you see an x in the equation, you should get back the original equation, f of x. So let's just kind of go back to that example that we had looked at. That example was our y value was equal to x squared minus 9. So y, f of x is just another way to name our function of y, another way to write y. So we could say f of x is equal to x squared minus 9. So if I want to find f of negative x, you're going back into the original equation, and wherever you see in x in that original equation, you're plugging in negative x. And then you're going to simplify. So I'm going to just put parentheses wherever I see an x in that equation, and rewrite everything else down, and then go back and plug in negative x where I add the parentheses. So we get negative x quantity squared is minus 9. Well, if you looked at negative x minus x, or times negative x, well, negative x times negative x is positive x squared minus 9. So f of negative x is equal to, that was our original function we started with, therefore, f of x is symmetrical across the y-axis. Okay, so to be symmetrical across the x-axis. Oops. So if we have a graph and something is symmetrical across the x-axis, basically think of it as if you folded your paper on the x-axis, there would be a mirror image of the graph. They would they lie on top of each other. So for instance, a sideways parabola where that vertex is at the origin, if we folded our paper across this x-axis, they would lie on top of each other. And so let's think about it. If we have some point here, this is our value, maybe x sub 1, here, y sub 1. If I flip this over the x-axis, my x value of my point is not changing. It's still x sub 1, but my y value of my point is now no longer positive y sub 1, it's going to be negative y sub 1. Or vice versa, if I chose this point down here, x sub 1 negative y sub 1, and I flipped it across, the negative of negative gives me that positive y sub 1. So we can say that if xy is a point, then a following point that has to be on the graph is x negative y. So this has to be true to be symmetrical across the y-axis. So another way to say that, if we think of y as f of x, so if we add that point x, f of x, this is the same thing as saying x negative f of x. So if we can, to test a equation, if you can plug in negative f of x or negative y into the equation, for either f of x or y. And it remains unchanged.
Hello?
Yeah,
Home.
what's for lunch?
I have class right now, Dad. Call Gianna.
You have practice?
I have class. Call
Mhm.
Gianna.
Okay. Sorry. Got a little sidetracked there. So if you can plug in negative f of x or negative y into an equation for f of x or y, and it remains unchanged, then the graph is symmetrical across the y-axis. So for instance, let's try an example to see. So the following example says, list the intercept and test for symmetry of the following equations. So let's test first for symmetry. So test for symmetry. Actually, yeah. Test for symmetry. So let's say for 4x squared plus y squared equals 4. Okay, so for across the x-axis, like we just talked about, we're going to plug in negative y for y. So if we go back into this equation and we plug in negative y for y, so we have 4x squared plus, I'm going to put a parentheses where the y is, quantity squared equals 4. And so replace that and plug in a negative y into that parentheses. Well, notice that we can simplify this a little bit. Negative y times negative y, that's the same thing as positive y squared. So we could rewrite this as 4x squared plus y squared equals 4. So looking to see if it's symmetrical across the y-axis, this is the same, sorry, x-axis. And so yes. So across the y-axis, well, if we plug in, we're going to plug in negative x for x. So doing that, we have 4, you see an x, put parentheses, we're going to square it, plus y squared equals 4. So same reasoning as above, when we square a negative, that's going to become positive, and so that ends up being the same thing. So we get 4x squared plus y squared equals 4. So let's find our intercepts. And let's see if we can graph this. So x-intercept, we're going to let y equals 0. Okay, so our original equation, we had 4x squared plus, I'm going to let y equals 0, so I'm going to replace that with a parentheses, squared equals 4. So if we 4x squared plus 0 squared, so we got 4x squared equals 4. So I notice it's quadratic. I notice a couple ways I can do this because it's a perfect square. On the one side, we could use the square root method. So let's just divide both sides by 4. We get x squared equals 1. Take the square root of both sides. We get x is equal to plus or minus the square root of 1, which is 1. Which we know because it was symmetrical across the y-axis that has to be the case, that if we had one value of our x and our y value, the negative value of our x and the same y value had to be a point. So the y-intercept, if we plug in 0 for x, so let x equals 0. So we have 4 times parentheses, we're going to put 0 in there, squared plus y squared equals 4. And so we see that y squared is just equal to 4. We can again use the square root method, or we can set it equal to 0 and factor. But using the square root method is faster. So we get y is plus or minus the square root of 4, or y is equal to positive and negative 2. So 0, 2, and 0, negative 2 are points. Which again, because of symmetry, that should have been the case. That the same x value, we would get the same or opposite y values. So far we have points at 0, 2, 0, negative 2, 0, 1, and 0, negative 0, and negative 1, 0. It actually didn't tell us to graph it. It just wanted x, y intercepts and symmetry. Later on in this class, this is a conic section. We're going to be going over those. That's the same thing when we were doing sideways parabolas. We're going to find that this is actually called an ellipse. And the way that it was written, we'll be able to tell that the center here is the origin. We would have been able to find these points too. And those are major and minor vertices, but that's just something to look forward to in a few weeks. So notice we fold the paper on the x-axis, it's a mirror image. Fold the paper on the y-axis, it's a mirror image. It's actually, if you folded that paper in force on the x and then the y-axis, or the y and then the x-axis, notice it would be a mirror image. This is actually symmetrical across the origin. So that's the last type of symmetry. So something can be symmetrical across the origin. So basically that's saying if xy is a point, on the graph, then negative x comma negative y is also a point. On the graph. So to test it, if we can plug in negative x for x, negative y for y, and doing that and simplifying, we get the original equation that we started with. It's symmetrical across the origin. So to test an equation, plug in negative x for x and negative y for y, and see if you get the original equation back. So question, I'm curious, does that mean, or do you think that would mean that if it's symmetrical across both the, if it's symmetrical across the origin, does that mean that it has to be symmetrical across both x and y axis at the same time? What do you think? Think about it. Could you come up with an example, maybe that where that couldn't happen? So we just saw when it was symmetrical across both, it was also symmetrical across the origin. And again, what I'm asking is, can it go the opposite direction? If it's symmetrical across the origin, can we say that it has to be symmetrical across both the x and the y axis? That's
Yeah.
so noisy. You
It
think so?
Yeah.
I would think so too. But it's not. It's not. So let me give you an example real quick. And it will show you why. So what if we had, well, I just told you that it's going to be across the origin and not the other, but let's just show it. So y equals x cubed. So if I plug in, so symmetry, let's just across the x-axis. After writing on this, my thing tends to have problems. Okay. For a little while. Okay, so we're testing across. Okay, so if we're doing the symmetry across the x-axis, then what are we doing? We're letting y be negative y. So if I did that and I plugged in negative y for y, I get negative y equals x cubed. But notice if I could get y by itself, if I got y by itself and multiply both sides by -1 or divide by -1, I would get y is equal to negative x cubed. And this is not the same. Oops. So it's not across the y-axis. Sorry, it's not across the x-axis. Okay, so y-axis, we're gonna let x equal negative x and see if it remains unchanged. Well, we have y is equal to, plugging in negative x for the x. Well, if we cube negative x times negative x times negative x, this is equivalent to negative outside of x cubed. So notice that if I looked at this and compare it to my original equation, again, it's not the same. So this is not symmetrical across the y-axis. So origin. So we're going to let x equal negative x and y equal negative y. So if we plug that in, we get negative y. This is equal to, I see an x there, plug in negative x quantity cubed. Well, this gives me negative y equals negative x. I can pull the negative out because I'm cubing the negative one. Another way to think of it gives me negative 1 out front. X cubed, get rid of the negative in front of the y. If we multiply both sides by negative 1 or divide both sides by negative 1, we get y equals x cubed. So this time we got it, and it is the same. So yes, symmetrical across the origin. So if we wanted to graph it, so we know if x, y is a point, we find one point, we know another point. We know negative x, negative y is also a point. Well, intercepts, if I let x equal 0, I get back 0. So 0, 0 is a point. If I plug in 1 and I cube 1, I get back 1. But because of symmetry, I can, without even doing the math, not that bad right there, I can say negative 1 is a point. If I plug in 2 for x and I cube it, so 2 cubed is 8. So I also know negative 2, negative 8 is also a point on my graph. Okay, so we got 1, 1, we got 2, 8. We have negative 1, and we have negative 2, negative 8. So if we folded our paper in quarters, notice that that would be a mirror image across each other. But if we just folded it across the y-axis, it's not a mirror image. Or if we just folded it across the x-axis, it's not a mirror image. So here's a case where it's symmetrical across the origin, but not both. I'm just curious what shapes they want you guys to know. So if we had a picture that looked like the following, at negative pi on the x-axis, we get back -1 on the y-axis. At pi halves, is crossing the x-axis. At 0, we have a point at 1. At pi halves, we have a point at pi half 0 and pi -1. So basically you're given the picture. So the graph of the equation is given. Find the intercepts, indicate whether the graph is symmetrical with respect to the x-axis, the y-axis, the origin, or none of these. Okay, so given this picture, what are the x-intercepts? So it's basically identifying that you know how to look at a graph and tell that it's symmetrical, what it means for x-intercepts. And so x-intercepts are the ones where the points are either crossing or touching, the graph is crossing or touching the x-axis. And so the 2 points we have are negative pi halves, comma 0, and pi halves 0. So when you're doing this on my math lab, see how they want the answer. See if they just want the x value of the intercept or if they're asking for the point. Because if they're asking for one and you get the other, it's going to be marked wrong. And so part B, our y-intercept, well, that's where the graph is either crossing or touching the y-axis. And so the y-intercept, we have 1 point where it's crossing the y-axis, and that is when x is 0, y is 1. And I never put in that value. Is there symmetry? If so, where is it symmetrical? What is it symmetrical to? So if we take that and we folded our paper across that y-axis, right, we'd have a mirror image. So it's symmetrical to the y-axis. I notice if I flip it here though, that's not going to give me the same thing. But if I flip it, let's see, in force, is that going to give me the same thing? So it's only symmetrical to the y-axis. One more. So you're given the picture. And if I describe when I'm telling you the picture where the points are, then I'm giving you the answer. So I can't do that. Okay, so looking at the picture, you should be able to identify what the x-intercept is, what the y-intercept is, and if there's any symmetry, what is it? So x-intercepts, where it's crossing the x-axis. So we actually have 3 places where it's crossing the x-axis. So that's at -4, 0, 0, 0, the origin, and 4, 0. The y-intercept, it's where it's crossing the y-axis. There's only one y-intercept, and it's the origin, 0, 0. So I noticed if I folded my paper across the y-axis, that hump would be over here, this hump would be down there. So that's not going to work. Same thing, it's not going to work to go across the x-axis. But if we folded it in fours, this is going to be lying on this. And so this is symmetrical across the origin. So if you're given a graph and it only gives you part of the graph, you should be able to complete the rest of the graph. So maybe let's say you have a point at -4, 0. How about -3, 2? Let's back down, -2, 0. And -1, 2. Back to 0, 0. Okay, and you're given that you're asked to complete the picture. Knowing this is symmetrical. Across the origin. So origin, if we have a point xy, then -x, -y also has to be a point. And so we also can see that we have points, we can determine points by looking at the graph. I see we have a point at -4, 0. So that has to change the signs on both of those. That is 4, 0. I see I have a point at -3, +2. So if I change the signs on that, that's +3, -2. So I'd have a point down here. -2, 0. Changing the signs become 2, 0. -1, -2 becomes +1, 2. So we completed the graph that would make that symmetrical across the origin. You guys have any questions on that? Okay, I'm going to change the page real quick and we're going to go to the next section. And now we're looking at lines. So you should be able to find the intercept. You should be able to find a slope of a line. You should be able to find an equation of a line given information about a line. You should be able to find vertical lines, horizontal lines, lines that are perpendicular or parallel to other lines, equations that are perpendicular or parallel to other lines. So equations of lines. So there's different forms of how we can write lines. Sometimes you see them in the form of ax plus bx, ax plus by is equal to c. A lot of times though, if you rewrite it and you solve for y, you have y is equal to mx plus b, another form of how they write it. When it's in this form, this tells us a lot of things about the graph. M is equal to the slope of the line. This actually gives us kind of directions on how to get to other points on a graph given one of them. Recall slope. I don't know if you guys remember this, the rise over the run. You might have heard it call that. So the slope, the number in our numerator is telling us how much we're rising or falling from the point we know on the line. And the run is telling us how much we're moving over left or right, depending on from the point that we're given on the line. So rise, well, rising and falling are your y values of your graph. So to find that, if you're given 2 points, you can look at the difference of your y value. All over the run is the x value. So all over the difference in your x value. So as long as you're consistent with which point you're starting with in the numerator, you start with that same value for the x in the denominator for that point. So I would get the same result if I had chosen, when I'm saying y sub 1 minus y sub 2 when I looked at the points. But this would have to be starting with x sub 1 instead. So when it's in that form, we can tell what the slope is, but we also can tell what the y-intercept is, right? We just talked about y-intercepts occur when x is 0. If you plug in 0 for x there, m, the slope, times 0 is 0. And so you'd just be left with your constant b. And so we have our y-intercept when it's in this form is at 0b. So a lot of times if we are given an equation of a line, we want to rewrite it as y equals, and that way it's just a lot faster way of graphing lines than having to just sit there and plug in values for x or y and figure out what the other variable would be. Sometimes you have another form of an equation of a line, so I'm kind of giving you different forms of equations of lines. You'll see it as y minus y sub 1 is equal to m times x minus x of 1. So they actually kind of have different names too. The first one, that equation of the line is standard form. So if they ask you to put your answer in standard form, that's what they want. They want you to get your x and the y terms to one side and all the other variables to the other, and the constant to the other side. This other one, y equals mx plus b, this is called our slope-intercept form. And the one I just gave you, y minus y sub 1 equals m times x minus x sub 1, this is our point slope form. And in this form, x sub 1 and y sub 1 is a point on the line, and m is equal to the slope. So if it says graph a line that has a point let's say at 2, 4, and a slope of negative 3/4. So because we're given a point, we're good, and we can graph this, and we're given the slope. And so we want to plot the point 2, 4. Horizontal axis is your x-axis, vertical is your y-axis, always in the form xy. So go over 2 and up 4. So from that point, the slope has given us directions on how to get other points. So if you have a negative slope, it doesn't matter where you put the negative. You can either put it in the numerator. We can treat this as negative 3 over positive 4, or we can treat this as 3 over negative 4. We can't put the negative in both places because that would make that a positive number, but choose one of them. So this one, when we first did negative 3 in the numerator, this would be telling me to fall 3 places. And this 4 is telling me to run, and it's positive, so go 4 places to the right. So from here, if I fall 3 places, and then I run over 4 places, yeah. That would be where I'm going to place my new point. Where if I used the other directions, this is telling me I'm rising 3, and I'm going to the left 4. So if I start here, if I rise up 3 and run to the left 4. I get a point here. So normally you don't put those squiggly lines in there. And so usually after 3 points is enough, and we can draw a line. So the other thing you need to be able to do is, given information about a line, you should be able to find the equation of the line. So let's look at the same problem. Given that we know that our slope is -3/4 and we have a point at 2, 4, we want to find the equation of the line. So there's a couple ways that you can do that. We can use that point slope formula, and a lot of times, and especially if you see the help feature, you might see it done that way. I personally like to use the slope-intercept form. Basically, the slope-intercept form, y = mx plus b. We have